Okay, so this problem is about wave in deep water. So we kind of talked about that a little bit in this section that is on hyperbolic trig functions. But this doesn't have anything to do with hyperbolic trig. This is really a limits question. So remember limits from really early in the semester. And it's also an optimization question. So we have this equation. So the velocity of a wave in deep water can be expressed like this. So 2 and 3 are constants that depend on the nature of the fluid, like whether it's an ocean of motor oil or an ocean of ammonia or something like that. And L gives you the length of the wave, and if you know the length of the wave, then assuming the water is deep, the velocity is given by that. All right, so these first two questions, like I said, are just limit questions. I guess maybe you could write this in fancier form. This is the same question as what is the limit as L goes to infinity of V? So what is it? Really, you just ask yourself what happens to each of these two internal parts. So as L goes to infinity, L over 3 goes to infinity, right? Because if you have a million bajillion divided by 3, it's still a really huge number. And as L goes to infinity, 3 over L, so that's the other little component under the radical here, is going to be 3 over a really huge number, and it's going to be 0. Okay, so you can just plug it into your calculator. What happens when you divide 3 by a million? It's practically 0. So what happens to the whole thing? So the whole thing, you end up with basically something like 2 times the square root of infinity. So what happens when you take the square root of a really big number? You get a really big number, right? And you can see this actually from the graph of the square root function. So what happens to the square root as x goes to infinity? Well, it happens slowly, but as x goes to infinity, the square root also goes to infinity. So what happens to this whole thing is the velocity goes to infinity. So the answer to A here, as L goes to infinity, V goes to infinity. So now we're going to play kind of a similar game with this second part. It says, what happens to velocity as L goes to 0? So take a look at the function. Probably a lot of people can just see, right? So as L goes to 0, this part, L over 3, is going to go to 0. Okay, so L over 3 is vanishing. But this part is getting huge because 3 over a really small positive number, why don't you just try that, like 3 over 0.000001. Why don't you plug that into your calculator? And it will be enormous, because if you have something like 3 over 10 to the minus 7, so 10 to the minus 7 is a really small number, right? It's the same thing as 10 to the 7th times 3, so it's like 30 million. So I hope that makes sense. So this part is going to infinity. So what you're getting again is sort of 2 times the square root of infinity. I'm wincing a little bit when I write that. I'm not supposed to write that. But again, 2 times what happens to the square root function as the input becomes infinite, the output also becomes infinite. So this is kind of like equals infinity. But that's so wrong to write that I have to rub this out, and I'm going to flagellate myself after this video is over. So what happens as L goes to 0? So I didn't say anything about this positive part, but that just means from the right? Because what is a negative wavelength that makes my head hurt? So only the positive ones make sense. So this means going to 0 from the right, okay, from the positive numbers. So as we just saw, as L goes to 0, V goes to infinity. So just to recap here, V also went to infinity in this case, right? So if I can draw some axes, so is it always infinity? No, it's not always infinity, okay, because just plug in 1. what happens when you plug in 1? You get a perfectly normal number, right? Like 2 times the square root of 1/3 plus 3. So I don't know what that is, but it's some perfectly good finite number. So I have a guess as to what this function looks like. And it's so embarrassing when you draw a line that's not even straight enough to look like a straight line. But what the function must look like is this, okay? So let's just start here at 1. So this is that perfectly sane value that we just found. And we know that as the wavelength goes to 0, the function goes to infinity. And as the wavelength goes to infinity, the velocity goes to infinity. So the way I drew it, it looks like the smallest possible velocity is at 1, but it's not. I just made that up. But in this last part, let's find out what is the length of the wave that gives minimum velocity. All right. So it's a minimization question. So something from the optimization chapter. Let me copy the function down here so I can see it. This v equals 2 times the square root of L over 3 plus 3L. Okay. So what's our plan here? Our plan is to take the derivative, set it equal to 0, and solve. And hopefully there's only one solution. And since I've done this problem before, I know that there's only one solution. And so that must be the minimum. So let's do it. What is v prime? And also another little subtlety here. We're doing minimization of an increasing function with positive values. So you could actually solve the simpler problem of minimizing v squared. So v squared is equal to 4 times L over 3 plus 3L. So I'll just leave it to you to check that if you take the derivative of this simpler thing and set it equal to 0 and solve, then you'll get exactly the same solution. But after teaching it a couple times, I think people find this fact even more baffling than just taking the derivative of something with a radical in it. So let's just do it the hard way. So v equals this. So what is dv dl, otherwise known as v prime? So the 1/2 comes down and kills the 2. So the 1/2 killed the 2. That's what happened to him. Now I've got L over 3 plus 3 over L. And this is all now to the minus 1/2 power. And I owe the derivative of the inside stuff. So this part just becomes 1/3. And you can do this on your own. I've done it this way a lot of times in class now, so I think you can probably done arguing with me when I do that, right? That should be clear now. So that's the derivative of 3 over L, and set this equal to 0. Alright, so remember what this negative, the negative means that it's in the denominator, right? So I have the square root of L over 3 plus 3 over L over 1/3 minus 3 over L squared, and this is equal to 0. So if I want to find the solutions of this, I can just look at the top. So I'll set the top equal to 0. So 1 over 3 over L squared equals 0. Okay. So how am I going to solve that? I'm going to multiply both sides by L squared. Okay, so multiply by L squared. Yeah, that's right. And then L squared times 0 is 0, and over here I get 1/3 L squared. They cancel here, which is the whole point. And now I have this equation. Solve for L squared, and you get L squared equals, so move the 3 over, becomes positive. Multiply by 3 to kill this thing, and you get 9. And you take the square root of both sides. Should be plus or minus, but we're doing a physics problem, so it must be the positive root, which is 3. Okay. And that's it. That's all. And some of you that are really careful might say, well, if the denominator comes out to be 0, then the derivative won't exist. And so that could also be a critical point. And you're right. Whoops. Whoa, my tablet just freaked out. But we don't have to worry about that really, because we're only considering positive values of L, and you believe that whenever L is positive, this thing is not going to be 0, right? Because positive plus positive is positive. So that's not something we have to worry about, and the answer for C is 3, and that solves the whole problem.